Hello everyone, welcome to my presentation about impact performance of 3D printed Kevlar fiber reinforced composites. First of all, let me introduce myself. My name is Emre Oflaz and I am PhD student in Mechanical Engineering Department in TOBB University of Economics and Technology in Ankara, Turkey. And also I am a research assistant in Mechatronics Engineering Department in Ketsuya Karata University in Konya, Turkey. In this presentation, my topics are additive manufacturing and direct ink writing, direct ink writing of thermoset composite samples, ASTM standards and sample design, impact test, and results and discussion. Additive manufacturing, also known as 3D printing, is a fast-growing manufacturing technology. As you all know, additive manufacturing allows us to fabricate complex geometries cost-efficiently and rapidly via layer-by-layer deposition. But beside all these good features, AM also offers low mechanical and thermal properties, as the basic process begins with the use of thermoplastic materials like ABS and PLA, which are very easy to use and cheap. But thermoplastic printing is based on repeated melting and cooling process, and it causes slow bonding between layers and lines. Because of this, mechanical properties of printed samples are generally lower than feedstock materials' mechanical properties. To overcome that mechanical and thermal drawbacks of the thermoplastics, thermoset polymers can be used. Thermoset polymers can be used in additive manufacturing via direct ink writing. Direct ink writing is a new method which based on extruding an ink whose viscosity is adjusted to be self-supporting during and after printing. As you can see on the right side, there is an extruding nozzle. With the nozzle, we can deposit our feedstock materials, we call it as ink. And as you can see below, extruded material remains its shape during and after printing. Ink for thermoset polymer composites. Thermoset polymer composites can be fabricated with direct ink writing, but first stage of printing thermoset polymer composite is to prepare a printable ink. A printable ink includes epoxy resin as a thermoset polymer matrix and nanoclay as a rheology modifier. Rheology modifier has a crucial role in preparing ink because ink viscosity has crucial role in direct ink writing. To get a printable ink, ink viscosity must be adjusted carefully via rheology modifiers. And as a reinforcement, we use Kevlar fibers. And lastly, curing agent to complete thermal curing process. This is the stage for ink preparation. First, we add curing agent to epoxy and mix it. In this stage, we call that ink as pure epoxy. Pure epoxy ink has no rheology modifiers like nanoclay or no reinforcements like Kevlar fibers. Then we add nanoclay that ink and mix it. In this stage, we call that ink as base ink. Base ink has nanoclay rheology modifier but no fibers. After that, we add Kevlar fibers to that ink and mix that, and we get that final ink version, Kevlar fiber reinforced ink. To directly write that composite ink, first of all, we fill that ink to the air adjusted syringe, and after that, we adjust the air pressure and measure the ink extruded in 10 seconds to find ink velocity. After that, we calculate all the printing parameters. Then sample designs are done according to ASTM standards and G codes are generated. After that, 3D printing can be started. After all the samples are printed, all the samples are cured in oven. As I mentioned before, there is a repeated melting and cooling process in thermoplastic printing methods like fused filament deposition or etc. But in direct ink writing, there is just one heating process after printing called as curing. This curing process at the very end offers stronger bonding between printing lines and layers. Sample design and test setup. Samples were designed and tested according to ASTM D4812 standard, which is standard test method for unnotched cantilever beam impact resistance of plastics. In the standard, dimensions of the samples and orientation of the fibers are very important. These issues were given importance during sample design, and this is our test setup for impact test. Test specimens were placed and fixed between jaws as shown at the bottom of the figure. Tests were carried out for 1 joule ISO impact test hammer. And impact energy calculated by the machine software was seen and recorded on the test machine display in the left corner. Test samples. To examine the effect of fiber amount and nanoclay amount on impact performance of 3D printed composites, three main test groups with different nanoclay and Kevlar fiber amount were printed. First group is pure epoxy. Pure epoxy group contains no nanoclay or fiber. Since there is no rheology modifier, that ink is impossible to print. So all the samples, pure epoxy samples, were fabricated via molding. 5% base ink group contains 5% volume by ratio nanoclay but no fiber. In a similar way, 8% base ink group contains 8% nanoclay but no fiber. In 3.5% Kevlar fiber reinforced group contains 5% volume by ratio nanoclay and 3.5% volume by ratio Kevlar fiber. To prepare a printable ink, enough rheology modifier must be used to both adjust the ink viscosity and to get that ink mixed homogeneously. So we prepared all the fiber reinforced inks with 5% nanoclay to make a good comparison between test groups, to make a good comparison between base ink group and Kevlar fiber group. In a similar way, 6.3% Kevlar fiber group contains 5% nanoclay and 6.3% Kevlar fiber. Test results. Impact energy values of the test samples were obtained from software test machine. Then impact strength values were calculated as the ratio of impact energy and cross-section area of the specimen. The mean and standard deviation values are calculated and they can be seen as table on the left side and as graph on the right side. To compare difference between groups, Mann-Whitney U-tests were conducted and p-values of the heat comparison was obtained. P-value below 0.05 was considered as significantly different. Test results and discussion. As you can see, pure epoxy group had significantly the lowest mean impact strength among all the test groups, and we can say that nanoclay and fiber reinforcement have a significant positive effect of impact strength of 3D printed composite specimens. 5% base ink group has the highest average impact strength, but there is no significant difference between 6.3 Kevlar fiber group and 5% base ink group. 8% base ink group had a lower mean impact strength than 5% base ink group. 3.5% Kevlar fiber group had significantly lower mean impact strength than both 5% base ink group and 6.3 Kevlar fiber group. When all results are examined, the following conclusions can be reached. First of all, nanoclay and fiber reinforcements has a significant positive effect on impact strength, but there are some exceptions. The first one is about nanoclay. Increasing the nanoclay from 5% to 8% decreased the impact strength, which was associated with embrittlement, because obviously increasing nanoclay amount made specimens more brittle and it decreased our impact strength. The other important result is about Kevlar fiber loading. 3.5% Kevlar fiber group had a lower impact strength than 5% base ink group. Since 3.5 Kevlar ink was prepared by reinforcing 5% base ink group with Kevlar fibers, the expected situation here was that the Kevlar containing group had a higher values than 5% base ink group, but it didn't happen as expected. It's thought that this situation is caused by unwanted pores formed by fiber loading to the inks mixture. But when the Kevlar fiber amount increased to 6.3%, impact strength increased again to level of 5% base ink group, and which means that increasing Kevlar amount to a desired level, it eliminate the strength loss caused by unwanted pores and had a positive effect of impact strength. Before I finish my presentation, I should mention that I am thankful to Jakarta University and TOBB University of Economics and Technology for all PhD study opportunities. And I especially thank to University of Miami for giving me opportunity to use the laboratory facilities. And I am also thankful to TÜBİTAK, the Scientific and Technological Research Council of Turkey, for financial support. And thank you for listening to my presentation.